Welcome to this webinar about API-based data access concerns for enterprises. In this session, we will be discussing the importance of APIs in modern data management and how they can be leveraged by enterprises to access and exchange data in a secure, scalable, and controlled manner. We will also be covering some of the potential concerns that organizations should consider when using APIs, including issues around data security, compliance, and performance. I hope that this webinar will provide valuable insights and best practices for anyone looking to incorporate API-based data access into their business operations. I'm Kobe, and let's get started again. Many enterprises today operate on data. Be it data we are requested to process or even data about our operations and their outcomes, observing the data our ecosystem consumes and generates can prove crucial to our enterprise's business. However, data comes in many sizes and shapes, and throughout the life cycle of an operative use case in our system can be stored in various places and formats. To make things even more challenging, as our application is living and breathing, things can change in our data size, shape, and location. A mature and responsible enterprise should prepare for such life events. This session is exactly about how to provide measures for addressing such concerns while keeping our enterprise operations intact. In today's webinar, we will cover the following topics: application programming interfaces as a means for standardized, tested, and measured data access. Then we will move forward to talking about data contracts and their usage in APIs. Moving forward, we will talk about separating the concerns for managing data contracts from managing APIs. Eventually, we will get to the interesting part, which is a proposed architecture together with several enrichment components to cover security aspects, distributed result cache, instrumentation, logging, and testing as part of our CI/CD pipelines. Eventually, I will also leave some time for questions and answers. Application programming interfaces are a powerful tool for exposing functionality to users. They allow us to define, document, and agree upon the language our system speaks. Our users, in turn, need only be aware of the language of the system in order to utilize it. When discussing data, the language we agree upon has three main components. The first component is the application endpoint implementation. Application endpoints are the entry points into our actual business logic. For example, we might have a web service which exposes an endpoint for a method returning a product given a product ID. The endpoint might look something like this. Each application endpoint has a well-defined input structure and a well-defined return value. These are sometimes referred to as request and response objects. The second component of our API language is the transport, both layer and protocol. A transport is the means by which we expect our application endpoint to be invoked over. For example, our API endpoints could be expected to be invoked over a TCP connection using the HTTP protocol. It is important to understand that the same application might expose the exact same code over several endpoints and transports. For example, the same application endpoint can be exposed to users both via an SDK, software development kit library, and via RESTful API. The last component of our API language is a derivative of the first component, which is the endpoint definition, and is usually referred to as the data contract. A data contract is a subdefinition of our endpoint, which defines both the internal structure of data being passed as input to endpoints and received as a result from endpoints. In fact, data contracts are so important that we will shortly discuss them with elaboration. Before we do, let's take a quick look at an example service which exposes a simple API to a data retrieving service. So what we see here is a Swagger API documentation of a service for managing customers and transactions. Swagger is a popular way to document APIs and share them with consumers, though it is certainly not the only way. What we basically see is several API definitions, and these definitions are for API access over HTTP, and hence we see that each API definition contains both a root and an HTTP verb, such as post, get, patch, or delete. And we can look at another concrete example, and we can see that a consumer can perform an HTTP request with the get verb to the customer's route. Simple enough, right? So how does that serve us in achieving standardized, tested, and measured data access? In one word, structure. APIs provide a well-defined structure to our enterprise's data access. By writing and implementing the rules for how our data can and should be retrieved, we are creating a well-defined code base which implements the documented rules we expose to the world. This code base, which conforms to the external structure we've exposed, can and should be bound to a test library, which covers the expected behavior of our code. Our code, in turn, having clear entry points and clear expected output, can also be measured more easily, for example, by collecting metrics about each entry point usage. As we've just discussed, an API, application programming interface, is a set of rules and protocols that specifies how software components should interact with each other. It defines the interface that one software component, for example, a client, uses to communicate with another software component, for example, a server. In turn, a data contract is a formal agreement between a client and the server that defines the structure of the data that will be exchanged between them. It specifies the data types, fields, and other information that the client and server need to understand in order to communicate with each other effectively. The connection between an API and the data contract is that the API defines how the client and server will communicate with each other, while the data contract defines the structure of the data that will be exchanged between them. In other words, the API defines the how, while the data contract defines the what. For example, if a client wants to retrieve data from a server, it might send an HTTP request to the server's API endpoint, using the API's rules and protocols for formatting the request. The server would then respond with data that conforms to the structure specified in the data contract. The client would then be able to parse and use this data because it knows the structure of the data it will receive, as defined in the data contract. What you see here is a protobuf, a Google protobuf's sample for defining a data contract. And protobuf is more than a standard for defining data contracts. It also allows to define services that are then used via gRPC, which is out of the scope of this session. But what we see is a strongly typed definition for types that are then being used over the wire in our API calls as request and response objects in the as a data contract of request and response objects. The benefit of using tools such as protobuf is that they also include it's a complete ecosystem that includes compilers and tools for generating the code to generate your data contract creation and mutation using the programming language of your choice. So the mutual benefits of APIs and data contracts doesn't necessarily mean that they should be tightly coupled. In fact, there are several advantages for managing their life cycles separately. Let's enumerate some of these. So first, the separation between APIs and data contracts improves the design and maintainability. Having smaller modules with different responsibilities is a good practice everywhere, and it's also true when dealing with APIs and data contracts. This separation of concerns allows us to work on different aspects of the system separately. And talking about aspects, I'm talking about the aspect of transport and network versus the aspect of the actual data structure. These are completely different domains. They do touch each other, and the API uses the data contracts. So there is a dependency here. But as it happens, usually APIs tend to change less frequently than data contracts do. So it is beneficial to be able to work on them separately. Then data contracts can and should be versioned and shared. Now, why? Why data contracts should be versioned and shared? So many times we will develop a system, and we will develop an API for creating the entities, updating the entities, deleting and retrieving the entities. And the only thing that's going to change in this API is that a request object in it, in the data contract, a field name was changed or a field was added. That means that only the data contract changed, not the API. We want to version the data contract. We want to be able to increment the version of the data contract, and we'll shortly see in the architecture how I recommend to do it. But the data contract should be versioned and shared across teams that want to work with it. And this brings us to the last point, which is that users of the data contracts can be agnostic to the API. So if I'm giving my data contracts to the data science team, and they want to know how the data looks inside the database, and they have several terabytes of data, and the only thing they care about is getting this data and parsing it. They shouldn't be aware of the fact that we used HTTP transport or some other TCP connection to bring the data. It's not relevant to them. Why bother them with these details? And it's also true to developers. Sometimes the developer working on a specific area of the system, he doesn't necessarily need to be familiar with the gateway of the system, which is the API in this case. So being agnostic to the API can be very beneficial. So up to this point, we've discussed and hinted towards why and how API-based data access can be beneficial to your enterprise. We've seen that an API-based approach for data access can be an enabler for providing our system design positive properties. In particular, we understand that it allows us to standardize, test, and measure our data access in a manner which allows us to separate system concerns, which is a good thing, right? After all, how data is being accessed is a different question than what does the data look like. So at this point in time, I would like to propose a solution architecture for enterprises, which has served me well many times, and on which we can discuss additional aspects which will be beneficial to your enterprise successful operation. I will provide a top-down review of the proposed architecture, as in this case, it will allow us to better understand how user needs are translated into functional aspects in the solution architecture. At the very end of our system, there is an end user, which is in need of data. Our user received the documentation of the API our system offers, which happens to be exposed over a network connection to the internet using the HTTP protocol. So our user types the URL address for the data she wants into her browser's address line. In turn, the user's HTTP request is passed forward into a domain name system, a DNS, which resolves the correct web server address to pass the request to. The web server parses the HTTP request and routes the request into the correct service, which is responsible for fetching the data the user requested, the data resource accessor. In turn, our data resource accessor service fetches the actual data from a database and returns it to the web server, which returns it all the way back to the user. Please just allow me to point at the fact that the web server itself does not make any direct contact with the database. I am pointing this out as it is very important to separate concerns yet again. The web server is responsible for managing network access and routing requests to and from system services. It shouldn't be allowed to do anything else, nor keep any state in it. Similarly, the data resource accessor is responsible for accessing data and returning it. That's it. No state management, no familiarity with the network layer on which the data is then transferred on. This separation is an enabler for scaling system parts separately. In case we have a network congestion at the level of the web server, we can introduce another instance of a web server and route traffic to it. And exactly in the same manner, if our data resource accessor is having trouble handling all the requests to it, we can introduce an additional instance of it to the system and have it share the load. So, okay, so this seems simple enough, and I'm certain some of you have come to this solution architecture in the past as well. No real invention here. But is this all there is to it? No. Earlier, we've had a discussion about how APIs are enablers for a testable system. Yet I have shown nothing which relates to tests up to this point. So let's fix that. In order to test our data access code, we need to introduce a test library. This library should be versioned and tested together with each release of the data resource accessor. How can we achieve that? Well, one way of doing so is to have both entities depend on the same code library. Almost, but not yet done. What big component are we missing at this point? The data contracts. Let's add them. Please note how the data access library depends on the data contracts repository. Changes to the data contracts repository are immediately propagated to the data access library, which in turn reflects changes to it to the data access library tests. Any attempt to modify a data contract which results in a failed test can be stopped at compile time and not be rolled out to production. Now that we've drawn a functional skeleton of the proposed solution architecture, which is functional but certainly not yet complete for any responsible enterprise, let's do a quick recap of what we've seen thus far before we begin enriching the functional skeleton. The first thing we've noticed is that our data contracts and their versions are held in a code repository. The second thing was that our data access code library depends on the data contract repository and is sensitive to modifications in it. The third thing is the data access library has a dependent test library which is sensitive to changes in it. We have a service in our system, a stateless data resource accessor, which depends on the data access library. Almost last, the data resource accessor is accessed via a stateless web server. And lastly, we've seen that both the data resource accessor and the web server can be scaled to run in more than one concurrent instance. Okay, so at this point, we are ready to move forward to complementing our solution architecture with several missing parts. Let us begin with the security aspects of accessing our enterprise's data. Not every request made to our API should be served, and maybe not all requests should even be allowed to enter our system to begin with. To do so, we need to introduce two security measures to our system. The first is an authentication mechanism, which allows us to verify that the request being made is indeed made by the entity which claims to have made the request. Authentication mechanisms are usually better placed at the entry of our system. In our case, it is the web server. Next, once our system knows that the requesting entity is indeed who it claims to be, we can make sure this entity is indeed authorized to make the request for data it made. Again, sooner is better. So let's add the authorization code to the data resource accessor. So we've authenticated and authorized the users which make requests to our API. That's great. Let's talk about another improvement which should be made to our proposed solution architecture. Requests for same data can many times be repeated without the result dataset actually changing. A common truth in the data world is that for most use cases, interesting data tends to get queried a lot and modified much less. This fact, combined with the overhead of accessing a database system for reading data, makes it very reasonable and efficient to store query results in an efficient distributed cache. By doing so, we can make sure that our data resource accessor can return query results directly from cache, instead of reaching out to a database system and having it compute the data we requested. Please keep in mind that in case a query result needs to be changed, it is the responsibility of the data resource accessor to invalidate the cache so that following requests will reach the database. Now, why did I say distributed cache and not merely cache? The reason for this is mostly the system's scalability and fault tolerance. By keeping our data resource accessor stateless, which I've mentioned earlier, we can verify that if a certain query result was invalidated in one data resource accessor instance, another data resource accessor will know about it and reach for the database to get the data it needs. This is very important, and I've seen it left out of system architectures many times. Be smarter and use a distributed cache together with cache invalidation. Okay, let me just check it on the chat, see if there are something. Before we proceed to the next concern, if there is any issue someone wants me to address, and I will have a lot of time for questions at the end, but if something is critically unclear, I will stop now. Or shall we proceed? Okay, so let's jump into the next concern. Our users' data access patterns and their experience doing so is very important. In fact, it is crucial. Instrumenting our system provides a visibility into the way our system is being used and hints towards bottlenecks, problematic areas, and maybe even redundant features and data. What should we instrument in an API-based data access solution? Well, I would say that there are several most interesting general usage metrics. The first usage metric is access to our system. Be it authorized or not, we want to know when someone knocks at our door. Usually the place to instrument the first contact an entity has made with our system is the web server. The second usage metric is actual access to the data resource accessor. Here we want to measure not only requests for data being made, but also which were resolved by accessing the distributed cache and which were resolved by accessing the database. We also want to know the total result dataset size, which will allow us to mitigate a buildup of a bottleneck in our system. Don't forget to instrument request latency for exactly the same reason. A very important instrumentation-worthy metric is errors which arise while accessing our API-based data access solution. A user having difficulty using the system is not something we should ignore. In some cases, such errors could even hint towards a security breach to our data. So, a related but different enterprise concern for API-based data access I wish to discuss is logging. But Kobe, wait, didn't we just log everything that happens in the system? Well, no. Instrumentation and logging are two different things. When instrumenting use cases, we are usually counting and measuring our system's behavior. Metrics are meant to be lightweight and provide a lens to the statistical behavior of our system. Logging is mostly the act of documenting non-countable and measurable important information as our system is being activated. For example, the measurement of the number of errors our system is experiencing when a specific API is being invoked might tell us that something is wrong with a specific area of an API. But looking at the logs will tell us what is wrong with the API. So why not simply log everything? Well, two main reasons. The first reason is that logging, due to the fact that it involves persisting data to a file system, has a high cost in terms of both latency and storage. The second reason is that logs, while being interesting, are a story we have to read. And reading takes more time than looking at a graph describing our system's behavior. That means that logging is mostly for researching our system's behavior and documenting its normal behavior, or for when something goes wrong, and usually both. From my last statement arises the answer to where we should place logs in our API-based data access system. For error logging, it's important to log the behavior of both the web server and the data resource accessor. For behavioral aspects of these entities, for example, initialization, configuration loading, connection to dependencies such as the distributed cache, again, we need to add relevant logs to both the web server and the data resource accessor. The last concern I would like to discuss is the concern of testing as part of our continuous integration and continuous deployment pipelines. This concern is the enabler for data contracts modifiability support during the life cycle of the system which data we expose. How so? Please assume that our API exposes a specific data contract version and everything is working as expected. Then, we modify a field name in a specific data contract and don't add or modify the data access library tests. Our CI/CD process, which runs the tests, does not detect that a breaking change has been introduced, and we roll out the new version of our data access library, which works with the new version of the data contract. Not good. Things will break for our users, or even worse, will not break, and they will get an invalid view of the data they asked for. For this reason, each modification we make to a data contract requires updating the data access library tests. Doing so will help us guarantee the completeness and correctness of the data we expose over an API to our users. So, thank you for bearing with me up to this point. I would like to conclude this session with a quick review of what we've seen in this webinar. We began with the observation that many enterprises today are relying on precise data availability. Then, we discussed how application programming interfaces, together with data contracts, can serve as a means to achieving this goal. Once in agreement, we've presented a proposed architecture for a solid and scalable implementation. Then, we've enriched the proposed architecture with critical elements for a responsible enterprise-grade implementation, such as authentication, authorization, instrumentation, distributed caching, logging, and testing. At this point in time, you should have a solid understanding of how a mature API for data access should be built. Before we move to the Q&A session, to the Q&A part of the session, I would like to first tell you that if you want to follow up on more content, some will be related to this topic and some will be related to other topics which are in the realm of distributed systems, then you can follow me on YouTube and on LinkedIn, connect with me or follow me however you feel comfortable. Thank you very much.